Okay, we're in section 11.3 here, and I'm going to do some more of that section. So the next thing to talk about is the multiplication rule for independent events. And that says if two events A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. Okay, now previously, just the regular multiplication rule said that probability of A and B is equal to the probability of A times the probability of B given A. Okay, but now we got the probability of A times the probability of B. The probability of A times the probability of B. Well, that's because the probability of B given A is equal to the probability of B. Okay, so which is what independence means. Okay, so independence means that the occurrence of one event does not affect the probability of another event. Okay, so like the example that I gave in the last video was let's suppose that you got a deck of cards at your desk, okay, and it's raining outside. Me telling you that it's raining outside has zero effect over whether you get an ace, right? Zero effect. So the probability of B given A is just equal to the probability of B. The probability of A given B is just equal to the probability of A. Okay? So even though you're given that information, that useless information that has zero effect over anything, okay? So let's take a look at problem 37. The probability that a randomly selected 40-year-old female will live to be 41 is 0.99855 according to the report there. Part A, what is the probability that two randomly selected 40-year-old females will live to be 41 years old? Okay, couple things here. So first of all, this is a multiplication rule type situation. Okay, and anytime you've got more than one event going on, and the word is and, you're going to have a multiplication rule situation. Okay, so and remember, if you're only selecting one item, it is not going to be a multiplication rule. Okay, so if the keyword is or not, okay, that's not going to be a multiplication rule situation. So we're going to select two randomly selected 40-year-old females. Okay, what's the probability that they both live to be 41 years old? Well, now the next thing to notice here is that I've got independent events going on. Okay, so 0.99855 is the probability that one female lives to be 41 years old. Okay, just because one person lives to be 41, that has zero effect over somebody else living to be 41. Zero. Okay, so I multiply by the same number again, 0.99855. Okay, in other words, this is a situation where I've got independent events going on. Okay, 0.99855 times itself gives me 0.9971. So it's very likely that two 40-year-old females will live to be 41. Very likely. Okay. Part B, what is the probability that five randomly selected 40-year-old females will live to be 41 years old? Okay. So again, I'm going to use the multiplication rule for independent events. Okay, and I have independent events going on. I just said that. So just because one person lives to be 41, that has zero effect over another person lived to be 41. So the probability is not going to change from person to person. Okay, I need five females living to be 41. Okay, so I raise 0.99855 to the fifth power, and that gives me 0.9928 roughly. Okay, so it's very likely that all five will live to be 41, okay, according to what we have calculated there. Problem 38 says that the packaging of an EPT pregnancy test states that the test is 99% accurate in detecting typical pregnancy hormone levels. Assume the probability that the test will correctly identify pregnancy is 0.99. Okay, and that 12 randomly selected pregnant women with typical hormone levels are each given the test. What is the probability that all 12 tests will be positive? Okay, so first of all, I'd recognize that I'm going to be using the multiplication rule. Okay, and I got 12 tests here. And now just because one pregnancy test tests positive, that has zero effect over another one testing positive. Okay, so the probability is not going to change from test to test. Okay, it's going to be 0.99 throughout. I need 12 tests to be positive, so I would simply raise 0.99 to the 12th power, and that would give me roughly 0.8864. Okay, so I got an 88.64% chance that all 12 would be positive tests. Okay. Problem 39 says among Americans who consider themselves auto racing fans, 59% identify NASCAR stock cars as their favorite type of racing. Suppose that 4 auto racing fans are randomly selected. What is the probability that all 4 will identify NASCAR stock cars as their favorite type of racing? Okay, so I have independent events. So just because one person likes NASCAR, that has zero effect over another person liking NASCAR, right? So I need all 4 NASCAR fans. Okay, well, 59% like NASCAR, and 0.59 to the 4th power then is what I'd want there. That would be roughly 0.1212. Okay, so that's a very low probability. So what that tells me is I got a 12.12% chance that I'm going to have all 4 NASCAR fans. Okay, if I have 4 racing fans in a group. Okay, so probably someone's going to not like NASCAR is what I gather from that. Okay. The next thing to notice here is that the conditional probability rule says that for any 2 events A and B, the probability of A given B is equal to the probability of A and B divided by the probability of B. Okay. Well, let's see here. So remember the multiplication rule. So the probability of A and B is equal to the probability of A times the probability of B given A. Okay, so what somebody has done for us is they've just taken, well, probability of A and B, that's equal to the probability of B and A, right? I can switch the 2 events and it's not going to matter. Like you're still talking about the same overlapping region on the Venn diagram. Now, if I switch the 2 events, okay, I'm going to have the probability of B times the probability of A given B. And if I divide both sides by the probability of B, probability of A and B divided by the probability of B, that'd be equal to the probability of A given B. Okay, so basically what I'm saying here is the conditional probability rule is not a new formula. It's just something that somebody has done where they've divided both sides by a number, and you end up getting this other formula here. Okay, so problem 40 says let A and B be 2 events with the probability of A equaling 0.3 and the probability of B equaling 0.4 and the probability of A and B equaling 0.2. Okay, part A, what is the probability of A given B? The probability of A given B, I'd use the multiplication or the conditional probability rule. That's equal to the probability of A and B divided by the probability of B. Probability of A and B, that's 0.2. Probability of B is 0.4. So if I take 0.2 divided by 0.4, that'd be 0.5 or 1/2. Okay. What is the probability of B given A? Okay, well, probability of B given A is equal to the probability of B and A divided by the probability of A. Whatever event you're given, in other words, whatever event is written second, you're going to be dividing by the probability of that event in the formula. Okay, so the probability of B and A, that's 0.2. That's the same thing as the probability of A and B. That's what I was just talking about. So, the key word is and, so you're still talking about the same overlapping region on the Venn diagram. Divided by the probability of A, that's 0.3. 0.2 divided by 0.3 is 2/3. Okay, so 0.67 roughly is going to be that probability. Part C, does the order of the events matter when writing a conditional probability? Yeah, they absolutely matter. So the probability of A given B is not the same as the probability of B given A. Okay, we see that. So yeah, it's going to matter how you write it. Okay. Part D, are A and B independent? Okay, well, remember what it means to be independent. It means that the probability of A given B has to be equal to the probability of A. Okay, so here's the probability of A given B that we computed, that's 0.5. Probability of A is 0.3. Well, that's not the same thing. Okay, so no, A and B are not independent. Okay, now you could have also looked at part B. Probability of B given A is 0.67. And by the way, if one of these are going to be, negative, then all of them are going to be negative. It's not like one's going to say one thing and the other's going to say, something different. Okay, so also the probability of B given A is 0.67 roughly. That's not the same as the probability of B, right? Probability of B is 0.4. Now you could, if you wanted to, use the multiplication rule for independent events. So I can only use this formula when I've got independent events going on. Okay, that's up here. Okay, I can only use that when I've got independent events. So the probability of A and B, well, that's equal to 0.2. Probability of A is 0.3. The probability of B is 0.4. So if I take 0.3 times 0.4, do I get 0.2? No, I get 0.12, okay, which is not the same. Okay, so if one is false, all three of these things are going to be false. If one is true, all three of these are going to be true, is kind of what I'm saying there. Okay. Problem 41 says, suppose that one card is randomly selected from a 52-card deck. Let E be the event that we draw an ace and F be the event that we draw a club. Okay. Part A, what is the probability of E? Well, the probability that we draw an ace, there's 4 aces in a deck out of the 52 cards total. 4 of 52 is 1/13. Okay, so there's nothing new there. That could have been in section 11.1. Okay. Part B, what is the probability of E given F? Okay, so I've got a conditional probability here, which means that I want to use the conditional probability rule. So the probability of E and F divided by the probability of F. Okay, so again, whatever event you're given, you're going to be dividing by the probability of that event in the formula. Okay, so let's see, the probability of F is the event that you draw a club. There's 13 clubs in a deck. Out of the 52 cards total, so 13 over 52 would be the probability of F. The probability of E and F. Okay, so what's the probability that you draw an ace and it's a club? Well, there's only going to be one of those cards, right? That'd be the ace of clubs. 1 out of 52. I'm dividing by a fraction, so the rule is to flip the denominator and multiply. And that'll allow me to cancel the 52s there, which is going to be 1 over 13. Okay, now, the main idea with a conditional probability is that the sample space is reduced in size. So, the thing to notice here is that I don't have all 52 cards in front of me. Okay, I only have the clubs. There's 13 clubs. What is the probability that in those 13 cards I draw an ace? Well, only one of them is going to be the ace, right? So 1 over 13 would be the answer. So, but I could have skipped all this and just went right to the answer, 1 over 13. Okay, so the main idea with a conditional probability is that your sample space is reduced in size. Okay, are E and F independent? Well, yeah, since the probability of E given F is 1 over 13. The probability of E, that's also 1 over 13. Okay, and by the way, I could have checked that the probability of F given E is equal to the probability of F. The probability of F is 1/4 if you simplify. So the probability of F given E would also be 1/4. Okay, I could have also checked that the probability of E and F is equal to the probability of E times the probability of F. So if I take 1/13 times 1/4, I get 1 over 52, which is the probability of E and F. That's also 1 over 52. Okay, so remember, if one of those statements is false, all of them are going to be false. If one of them is true, all of them are going to be true. It's not going to matter how you look at it there. Okay? Why don't we stop right there?